Hey all, the goal of this video is to remind you about how this valence shell electron repulsion theory works. And so once again, we have these molecules and we want to look to see how many atoms are bonded to the central atom. And so we see methane down here, which has 1, 2, 3, 4 hydrogens bound to carbon, but no lone pairs. We also have ammonia, which has only 3 things bound to that nitrogen, 1, 2, 3 hydrogens, but it also has this lone pair, and this lone pair also repels, so it pushes those other molecules, those other atoms I should say, of hydrogen away. And then here we have water, oxygen with 2 hydrogens, and it has 2 lone pairs according to our structural formula, and again those 2 pairs are going to push everything else away. And so it's this idea that electrons repel. And so in all 3 of these pictures, we see that everything is spacing themselves out as equally as possible. They're trying to get as far away from each other, whether it's an actual atom that's bonded or whether it's a lone pair. And so there's 2 things that are going to be important for us: the number of atoms bonded to the central atom, and also we want to pay attention to the number of lone pairs. And so if I skip ahead here, we're going to look at lone pairs are also important. These big blobs here are trying to represent the lone pairs, and we can just basically see that they too take up space. And so when we look at that, we get 5 basic shapes. A linear has 2 things bound and no lone pairs. We have a bent that has 2 atoms bound with at least 1 or 2 lone pairs. We have trigonal, which has 3 atoms bound to the central atom, but no lone pairs. We have trigonal, which has 1, 2, 3 bound to it, and a lone pair. And then finally tetrahedral, all 4 bonds, 0 lone pairs. And so we're going to use that data to try to figure out what our 3-dimensional picture is going to look like. And so we already went through a couple of these in class the other day, but here's just a recap of what we've been doing. And so we have this picture of carbon dioxide here, this linear picture looking at the first row. And so we can see the number of atoms bound to that central atom in linear is always going to be 2. So if you have 2 things bound, you really have 2 choices. It might be linear or it might be bent. If there are 0 lone pairs, now we look at the carbon here, right? There's no dots around that carbon. If there's 0 lone pairs, then we know that it's going to be a linear molecule. So we put the one outer atom on one side, one on the other, make it nice straight across, and we go from there. We can figure out if our bonds are polar or nonpolar, just like we did in the structural formulas. We can get our partial negatives because oxygen's pulling harder, partial positive because carbon's losing them. And again, as we talked about, because those poles are in equal but opposite directions, anytime a linear molecule has polar bonds, those polar bonds, if they're equal but opposite directions, will cancel out. But what if, when we drew our structural formula, we had 2 atoms bound to the central atom, but we also had lone pairs? And so we saw that model in water. So here, water, we have 2 atoms bound to the central atom, in this case hydrogen and hydrogen, but we have 2 lone pairs. You can kind of make out these 4 dots right here. Doesn't matter if we have just 1 pair of electrons or 2 pairs. Either way, those electrons are going to repulse or repel these hydrogens. And these hydrogens want to get as far away from possible from those scary little dots. And so they're not linear straight across, but instead those hydrogens are going to be pushed away from those lone pairs. And as a result, we get this bent shape. And once again, we figure out our polar bonds, and we can write in our arrows and show the direction of pull, and we can see that oxygen is going to be partially negative and the hydrogens are partially positive. But because both those arrows are being pulled upwards towards the oxygen, although the left and right will cancel out, that molecule is still going to have an overall pull. And so even if all the bonds are polar, well, the molecule will still be polar. Unlike our linear, those bonds are not going to cancel out. So then we move on and say, okay, so what if we have 3 atoms bound to the central atom? So when we have that, we're looking at possibly trigonal planar. We have 3 atoms bound, in this case fluorine, 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 and we have 0 lone pairs. BF3 happens to be an exception to the whole rule. We saw that early in our notes. NO3, -1 that we've been looking at, nitrate, is another example of a planar. And so in this case, because we have 0 lone pairs on this boron, and we have 3 things bound to it, it's going to be trigonal planar. And you could have probably predicted if these fluorines are going to try to get themselves as far away from each other as possible, you might have picked this arrangement with 120 degrees in between. We don't want to put one left and one right and one up because that would leave this whole empty space on the bottom. Instead, they say, okay, well, let's orientate ourselves. Let's push as far away as we can. And it's a little bit harder to visualize, but picture yourself being this boron, and you have fluorine pulling this direction and this direction and this direction on you. Those bonds, since they're all at 120 degrees, those poles are going to cancel out. And even though the bonds are polar, the molecule overall is going to become nonpolar. Once you have your structures drawn, once again, don't forget to figure out your bonds. You can see on this example, that's a very big difference in electronegativity. Really, really close to being ionic, yet they still just managed to pull off the sharing. So don't forget to add your partial negatives and partial positives. Well, sometimes we see that there might be 3 atoms bound to the central atom, but there's still a couple of electrons left over for that central guy. And in this case, we end up with a shape that we call pyramidal. And so pyramidal, once again, we have a 3, but this time we have some dots left over. And so if we look at ammonium here, we can see that ammonium has 1, 2, 3 hydrogens. But because of the number of valence electrons, nitrogen also got a couple of those valence electrons. And so we had those 2 dots. And remember the idea here, and the reason why it looks different from our trigonal planar up here is because those 2 electrons, those 2 dots push on those hydrogens and they repel them. And those hydrogens, rather than being spaced out at that nice 120 degrees, they all get pushed down. And if we were actually able to draw this in 3D a little bit better, you'd see that one of these hydrogens are actually coming out at you, and one of the hydrogens is actually kind of going out into the computer screen or back into the computer screen. But it's just kind of hard to draw that 3-dimensionally. But these pairs push on the other ones, and so we get a very different shape, all because of that one lone pair. And then we can probably visualize this all right. We have this arrow going kind of upper right towards nitrogen and upper left towards nitrogen and just straight up towards nitrogen. And once again, we maybe have a cancellation of lefts and rights, but all 3 arrows are pointing upwards. And so if we have these polar bonds, they will not cancel each other out. And in this case, we would get a directionality of straight up. And so if the bonds are polar, the molecule will also remain polar. So now we've seen if we have 2 things bound and 0, it's linear. 2 things bound and 1 or 2 lone pairs, it's bent. 3 atoms bound and 0 lone pairs, it's that trigonal planar. If there's 3 atoms bound and 1 lone pair, it's pyramidal. And our last major option is tetrahedral, when there are 4 atoms bound to the central atom, but 0 lone pairs left over. And we see this quite a bit because a lot of atoms, like carbon, they want to make 4 bonds, and that satisfies their octet rule. And so here we see CH4, and so we have 1, 2, 3, 4 hydrogens. And since we can only have 8 valence electrons in this picture, we don't add any extra dots. Carbon can't have any more than that 8 anyways. And so we get 4 and 0. And once again, those hydrogens are going to orientate themselves as far away from each other as possible. And drawn a little bit better, you can see that this arrow is trying to indicate that this hydrogen is coming out at you, and this hydrogen is kind of going back into the screen, and these 2 hydrogens are in the same kind of 2-dimensional plane. Now in this case, it happens to be all nonpolar bonds, and we learned that if you have nonpolar bonds, well, the molecule is going to be nonpolar. But regardless, even if they had polar bonds, because of their orientation and being equally this 109.5, they will actually cancel out. It's kind of hard to see, but if they're polar bonds, that molecule will be nonpolar. Finally, I won't worry too much about the trigonal bipyramidal. It's kind of an exception to the rule. Sometimes you can have 5 things. It's one of those exceptions we saw earlier. Phosphorus doesn't mind having a few extra valence electrons. We're not going to really worry about what this guy looks like. But you can kind of see it almost starts to look like a pinwheel, and those bonds will cancel out. But really, we're just going to worry about these first 4 shapes. So what you got to keep in mind is that you need to get your correct structural formula in order to be able to do this. Because in order to have if you have the correct structural formula, you can then choose correctly the number of atoms bound to the central atom and the correct number of lone pairs. And then you have to need to start memorizing what name goes with what shape. All right, draw the picture. It takes a slight tweak, slightly different angles and directions of your 3-dimensional or your 2-dimensional structural formulas. Add your arrows, add your tie bowls, and then you're done. So good luck with this. Keep practicing, and I'm sure you'll get the hang of it soon.